series around research into low global warming potential refrigerants. Today we'll be discussing predictive tools for refrigerant behaviors. And we have with us, on the next slide, we have with us the list of speakers. We have Ahmad Abuela and Dean Edwards, R&D Associate Staff Member in the Building Equipment Research Group at Oak Ridge National Laboratory. He has 14 years experience in thermal and power systems. Ahmad's area of expertise is in multifunctional heat pumps and energy storage. And his current research involves micro-combined heat and power, gas-fired heat pump water heaters, and hydro-pneumatic energy storage. Philip Johnson is a Senior Director of the Applied Development Center for Daikin Applied. He is a former chair and current member of AHRI SSPC 15, was a member of the Canina THSC 61D, Working Group 10 for UL CSA 60335-2-40 Edition 3, and has been involved in many AHRI TI flammable refrigerant research projects as a project monitoring subcommittee member. Greg Lanteris is an AHRI member and the group leader of the HVAC-R Equipment Performance Group at NIST, leading several projects on the flammability of low GWP refrigerants. He also contributes to the oversight of several refrigerant flammability projects funded by AHRI and AHRI. Previously, he worked for 25 years at NIST in the Fire Research Division, studying the chemistry of fire suppressants and flame retardants. And we thank you all for your help and for joining us today. And Ahmad, I did butcher your name, and I am very sorry about that. So Philip, thank you for introducing the series. Greg, if you could go to the next slide.
Okay, thank you, Helen. Sorry for that little delay there, but here's the list of speakers that we have today that Helen just introduced. And I'm going to give you an introduction to the webinar itself. So in terms of background, to date, most of the promising lower global warming potential refrigerants are flammable. And so implementation of these refrigerants in the field and actual applications requires revisions of relevant safety standards and codes. So to advance the understanding of flammable refrigerant safety, AHRI initiated its flammable refrigerants research program in 2016 to deliver scientific findings and produce publicly available technical references to support code and standards activities related to the use of these refrigerants. So AHRI has been leading this multi-million collaborative research program with substantial support from AHRI, the California Air Resources Board, and the U.S. Department of Energy. So today's webinar is going to focus on two of the research projects within this overall program that were funded by the Department of Energy. So there have, so this webinar on predictive tools is going to include some different types of simulation and modeling that have been conducted for flammable refrigerants. So some examples of those modeling efforts include, refrigerant physical properties that may be used for design, analysis, as well as for just operating and servicing equipment. But today's webinar is going to include discussion on the use of computational fluid dynamics, or CFD, to analyze the dispersion of refrigerant throughout a space in the event that it's inadvertently released or leaked. And then today we'll also hear about how combustion modeling is performed, at least in terms of the fundamental physics and chemistry at relatively small scales. But not covered today in combustion modeling would be work that's being done at larger scales, which then makes use of CFD to predict fire behavior. And then finally, another form of modeling not covered today would be various forms of quantified risk assessments, such as using fault tree analysis to model the risk involved in hazards. And that modeling typically relies on the above analyses, using CFD and combustion modeling to assess the probability and the severity of events. So the Oak Ridge National Labs modeling effort that we're going to talk about today, the primary purpose of that was to examine charge limits that are in safety standards for how much flammable refrigerant can be in a system. The scope of the project, though, was somewhat limited to what I would generally characterize as smaller scale systems. So in this case, that was a wall-mounted ductless split system, which covers a single room, included a ducted package system, where the ducts were distributing conditioned air to 4 different rooms, and then also the case of a small room air conditioner, again, just serving a single room. So the charge quantities, just for scale and magnitude, are listed to the right there. The phase 1 results were published in 2018, and there were 2 parts of that work in terms of reports. And then phase 2 kicked off in 2019 and continued and extended the work on wall mount ductless units. And in that case, it revised the range of input values to improve the reduced order model coverage for some more realistic scenarios. And then also is including cases with fan operating, whereas the original work, as published in part 2, did not include a reduced order model for fans operating. Then on to the NIST modeling effort. You're going to hear a little bit about the work that NIST has been doing to develop models that can predict the burning velocity for arbitrary mixtures of refrigerants. So as you may know, not all refrigerants are a single component. Some of them are blends of 2 or more components. A classic example being refrigerant 410A, that's widely used today as a mixture of R32, which is flammable, and R125, which is non-flame propagating. So potential future use of the tools that NIST is working on would assist future work beyond their current project to look at designing refrigerant blends where you attempt to meet multiple objectives, such as minimizing flammability, but trying to, say, maximize some other performance metrics, such as efficiency or capacity. And then other future use would be predicting the fire behavior of flammable refrigerants by improving some of the combustion process models. So with that, I'm going to turn over the presentation to Ahmad. Just a moment while I give up control. Okay, Ahmad.
Thanks, Phil. So I'm going to talk about the predictive tool that we're working on at, or on developing at ORNL, or Oak Ridge National Laboratory, ORNL. And on the next slide, yeah, so I'm going to go over why we're doing this and how we're doing it and what we have done so far. So to just rehash the problem, what we're trying to solve is how refrigerants move into a space when they're released into it. And how refrigerants are dispersed into a space affects the concentration in different areas of the space and affects how much of that refrigerant can be ignited. The dispersion problem is very complex because it has so many variables that play a part. The characteristics of the release itself, how high it's released from, the velocity of the release, the geometry of the space, is there air movement or not, ventilation or not, are there openings or not, and the properties of the refrigerant itself, how heavy it is, and such. So how do we predict how a refrigerant disperses when it's released? The most accurate way is to use a computational fluid dynamics simulation. And in those simulations, we divide up the space, the whole room, into very small cubes we call cells. And we solve the governing equations in each cell, and we compound the effects from one cell to the next in all directions. And we march in time doing that. And although this approach, the CFD, can provide very accurate, detailed information, it's got some limitations and drawbacks that makes it impractical for a standard developing body to use. So first of all, it requires very good knowledge of the physical phenomena and the software that's being used to simulate this phenomena. And it requires powerful computing resources, which may not be available to everyone. It takes a very long time to complete simulations because it could be the space could be divided into millions of cells, and we march in time with very small increments to have accurate results. So the ideal solution is to abstract the problem into a statistical model where we supply all the inputs, all the factors that influence the dispersion of the refrigerant into a space, and a purely mathematical model, we get the outputs. So we want a model that mimics reality without modeling that reality. So that's done by what we call black box approach. And in that approach, we pick a model, some model, and that model is basically a bunch of mathematical equations with a large number of coefficients, let's say. And we feed that model the inputs of those accurate CFD simulations and the outputs. And we train that model and change the coefficients and tune them to match the prediction of the model to the outputs of the CFD simulations that we had already done, and that's called training. So this is an ideal solution. It takes literally less than a second to run. You input a bunch of numbers, and one click, you get outputs. But of course, because we're not simulating the physics, there are limitations on that model. First of all, let's take a look at how it works. If the black line on the right, the top right graph there, if the black line is the actual physical phenomena and how it behaves, what we do is we pick points and train the model to predict those points. I skipped the slide there. Yeah. So that in itself, by definition, introduces two problems. Then what if we try to predict something that's outside the training bounds? The problem is we don't really know what the physical phenomena does outside those bounds. It could be, the model could be predicting that it's going up, but it's going down, or vice versa. The other problem is in between points, what happened to the physical phenomena? And that's associated with non-linearities in the physical phenomena. So if it changes suddenly between points or has very sudden changes, it may result in very large errors. So because of those limitations, the choice of the training points is very critical to having an accurate model in the end that can actually accurately mimic the reality of the phenomenon that we're simulating or trying to forecast. So we start with bounding our problem. So we've listed all the variables that we want to study the effect of. So those are all the influencing factors or our variables. On the right, there are the continuous variables, and this can take any value between the upper and lower bound. And we chose the bound, so we make sure that all the values of likely interest are bounded within those bounds. On the right, there are discrete, they're binary, 1 or 0 or on and off. So if the release is coming from an equipment, is the fan of the equipment running or not? And the direction of the release, is it the refrigerant is being released horizontally or blowing down or up? So we end up with 4 different models because of the discrete values. 2 for if the fan is off, and 2 if the fan is on. And for each one, the release could be horizontal or vertical. So now we're still trying to bound the problem and pick the values to use in the simulations, but what if the fan is on? What would be the flow rate of the fan at the equipment that we should use? And there are two standards that are most referred to. They're the UL and the IEC. Each one sets the minimum charge of the equipment and the flow rate of the fan of the equipment, and they're different between each other. So we wanted to make sure that we simulate the worst case. So we decided to do a screening study where we look at both cases, and on top of that, to see the effect of if there is a delay between when the release happens and the fan comes on. So we decided to make the screening study of using IEC charge with UL flow rates at different delays, and vice versa. And this is just to give you the idea of what we simulated. So it's a rectangular room. I'm sorry, it's 3 to 4 aspect ratio room with the return and supply near the top of the room. And it had about 1 million cell. So we have to solve the equations 1 million times every time step. That gives you an idea of how long this takes. And the results were with the UL charge and IEC flow rate and UL flow rate, and with the fan on and different delays, we didn't really see any difference in metrics of interest, the concentration, maximum concentration, and mean concentration, and the amount of flammable volume that's in the space. Same thing for using the IEC charge with different flow rates and different delays. We've not really seen any significant difference. And we've also studied the effect of the size of the cells or the mesh resolution. And again, smaller mesh predicted to a better accuracy the characteristics of the dispersion, but in terms of the metrics of interest that are the mean concentration, maximum concentration, amount of flammable volume, there was no significant difference. We also studied the effects, or studied different aspect ratios for the ventilation of the supply and return to see if there is any effect on the concentration value on the amount of flammable volume, and we didn't see any significant difference between them. So the findings of that campaign was to go with the coarse mesh that we call mesh 1 here because it's the fastest. And we decided to go with the IEC minimum because it has the larger charge, which is a worst case scenario. And we decided that the aspect ratio, or we found out that the aspect ratio of the vents doesn't impact the results, so we kept it as square. So now that we've bounded our problem and chose all the bounds, and we decided on an air flow rate and a charge setting of the equipment, we wanted to see how do we sample points for the training data set of the model. And as you can see from experience, we know that the results are more sensitive to some parameters or some variables more than others. So you see here, for some parameters like leak height, for example, we only have 2 levels. Ventilation, on the other hand, we have 5 levels, and that's because the results are more sensitive to the ventilation, because ventilation introduces more non-linearity in the results. We're estimating that for each reduced order model of the 4 will require between 2,000 to 3,000 cases, which is a lot of cases and takes a lot of time. So it's very important to have a feedback and reduce that number as much as we can. So currently we have, we're doing what we call parametric sweeps. So we hold one variable constant at the central point and sweep all the other parameters around it. That's a sensitivity analysis to see how the result is affected by changing each variable. And that the results of these sensitivity analyses we use to either reduce the levels of the variable that we're going to sample or increase it. We've added a lot more computational resources so we can have more than one model simulations running concurrently. In the end, I'd like to thank the Building Technologies Office of the DOE and especially Tony Buza for funding this work. And I'd like to thank the RT Project Monitoring Subcommittee for their guidance and feedback. And with that, I conclude my presentation and ready for questions.
Thank you very
Well,
much.
this is Phil Johnson.
Sorry, go ahead.
Go ahead, Helen, if you're going to.
No, please.
I think we'll cover a few questions that we've got in the Q&A box, if that would work right now, because our next speaker is not yet online. So we have a question from Carl. Helen, do you want to go ahead and
sure. Yeah. Thank you, Phil.
Does
the refrigerant have a pulse at the inlet, and does the refrigerant enter the room as a liquid or a gas? That was one of the questions from the listeners today.
The refrigerant enters the room as gas. It's vapor. Does it have a pulse at the inlet? I'm not sure what that means. Can we have a clarification on that?
Hopefully somebody will write back in with a clarification. So we'll hope for that will come forward. I'm going to switch to a new question, Ahmad. What kind of black box model do you plan to use? If it is deterministic, then there may be room to reduce the CFD simulation count significantly. For example, LHS and adaptive DOE. So these are very technical questions, Ahmad. So let me know if you'd like me to read that again.
Right. So we're using Tasmanian. It's a multi-dimensional regression tool that was developed at Oak Ridge National Laboratory. It's statistical, and it's you can think of it as piecewise interpolation tool.
Thank you, Ahmad. There's a couple of questions here, and I think that you or Dean may be able to answer. One is, do CFD simulations, were they validated with experiments? And Philip, this may be some things that you could help answer as well.
So they're not all of them, of course. We're talking about hundreds or thousands of simulations, but in the very beginning, we did a select number of experiments, and we validated our model against those experiments. So we know that the setup of the model, the choice of the turbulent model, for example, and boundary conditions are okay. They predict the experiments well.
Philip, would you be able to talk a little bit about some of the validation testing that was done around this? I can tell you that, one of the things that was very interesting to me, when I first looked at some of these results was, the part that density and ventilation play in the way that the refrigerant kind of moves across the room. And I know that there were some experiments done kind of looking at those things. Philip, I don't mean to put you on the spot, but is that something that you could talk about a little bit?
Certainly, yes. Yeah, as Ahmad mentioned, there was some physical testing conducted. So in the earlier parts of this project, Oak Ridge subcontracted some of the physical testing to another company. And the details are in their Part 1 report, which can be found online. And so the case that they studied in detail was the wall-mounted ductless system, where they did set up a space, created a diffuser to be the leak source. So they did have refrigerant flowing through a tube, controlled by a valve to set a flow rate or a leak rate, through a diffuser to kind of simulate what would happen inside an actual unit in terms of reducing velocity at the point of entry into the room or to the actual space being studied. And then within the room, they had an array of sensors to measure refrigerant concentration versus time and space as it moved throughout the room. So then those physical measurements were compared to the CFD results to validate the assumptions that went into the CFD models.
Thank you very much for that, Phil and Ahmad, and thank you for that excellent presentation. Our next speaker, Greg Lanteris, has joined us, and so he'll be presenting on his work related to this the examination of low global warming potential refrigerants. Greg?
I am here. Have you transferred the screen control over to me? Can you hear me?
Yeah, I think just request it, Greg, and then it'll transfer to you.
Okay. How do I? You are viewing Greg Lanteris' screen. How do I request it?
Hover your mouse over the view options right next to what you just read, or click.
Very good.
You're going to
View options, request remote control. Got it. Okay. Request. Thank you very much, Phil. Click to start the mouse. You are controlling Greg Baker's. Okay, somebody, I guess you guys will put my presentation up there, correct? Right now I see the Oak Ridge talk up there still.
You could just go to the next slide, Greg.
Yes. Okay, very good. Thank you. Okay, so the title is Modeling Tools for Flammability Ranking of Low GWP Refrigerant Blends. And as you all know, high in GWP working fluids will be phased down. The new low GWP working fluids tend to be flammable. There's typically, not always, there's a trade-off between flammability and GWP. If you make the compounds break down in the troposphere, you typically do things like add double bonds or hydrogens. That makes them have a lower GWP, but it also tends to make them more flammable. These compounds have high flame temperatures, and they're fairly reactive, but not as reactive as hydrocarbons because the chemistry is different. So they're typically on the border of flammability. That makes the understanding of their fire behavior more complicated and makes development of codes and standards more difficult and more challenging. And so if we can do things to understand how they behave, how the chemistry works, and how they behave in flames, that will help us move forward. So in the long term, we'd want to be able to predict the fire behavior of these flammable refrigerants. Now, that's a pretty difficult task, but not impossible. In the shorter term, we want to predict the laminar burning velocity of flammable refrigerants. The reason why is because that's the starting point for predicting fire behavior, flammability in general. If you can't predict the burning velocity, you probably can't predict very much about the real behavior in a fire in terms of extinction and propagation. So what is a burning velocity? Well, imagine you have a long tube filled with a flammable mixture, say 10% methane and 90% air, and you light it at one end. So you light it at this end, and the flame propagates down the tube. The rate at which the flame propagates through this pre-mixed combination of the fuel and air, that's called the laminar burning velocity. We sort of idealize it and say it's steady, laminar, planar, one-dimensional, infinite in the lateral dimensions, and adiabatic. And that's the reason we idealize it that way is because every experiment has deviations from this. And so every experiment will give you a different burning velocity to some extent, depending upon which things you've not made ideal. And so we can correct for all these things and then cross-compare the different experiments. I'll talk about that more later. But that's what laminar burning velocity is. Now, why is it useful? Well, it's a single parameter that combines the effects of energy release, heat and mass transfer, and the overall reaction rate. All these things control the propagation, and they control the behavior in a fire, too. So the laminar burning velocity, LBV, is proportional to the thermal diffusivity times the reaction rate to the square root power. Thermal diffusivity, we know. Overall reaction rate, that's where the Arrhenius behavior comes in. It depends upon the fuel and oxidizer concentration, so that's where the stoichiometry effect comes in. It's exponential in temperature, so that's why high temperature things tend to react faster. And this exponential factor, the activation energy, that sort of describes the chemistry. You know, if it doesn't react very well, then there's a higher activation energy, which is the case for the fluorinated compounds. They're reactive, but not as reactive as hydrocarbons. The burning velocity is useful for predicting a lot of practical things in combustion. The turbulent flame speed, the lean flame extinction, the overpressure hazard, the explosion hazard, quenching distance. If we could predict burning velocity, we can probably predict the E681 flammability test in the AHRI 34. So it's a really good parameter for understanding combustion behavior in general. And in the combustion community, everybody has really latched on to predicting burning velocity for hydrocarbons because it's generally a very useful sort of foundational parameter. Finally, it's being adopted in codes and standards in industry. So being able to predict it is useful. So again, the short-term goals of this particular project are to predict flammability of blends. Why? Well, everybody's going to blends, and then they want to optimize the blends. You know, you can calculate or estimate the performance of a blend in an actual piece of HVAC equipment in terms of its coefficient of performance, its volumetric capacity. You can estimate the toxicity, and you can estimate the GWP, but there's no good, accurate way of predicting the flammability of a blend. So you can't really optimize your blend or understand how it's going to behave in an actual piece of equipment ahead of time because we're stuck on flammability. So if we could predict the flammability, that would help us optimize the blends better instead of having to measure it all the time. And you know, with 5 components of a blend at variable compositions, that's a lot of things to have to do a lot of tests on. So if we could calculate it, that would be great. I just learned the Australians are pretty far ahead, and they're adopting these 2L refrigerants at a much higher rate than the U.S. is. And so they're starting to reclaim refrigerants, and they've got to transport this stuff around. And so they have mixtures of all these reclaimed refrigerants that they have to transport, and they have to understand the flammability in order to regulate and characterize the stuff we're transporting. And they told me that if they could predict the flammability of these arbitrary blends of refrigerants, that'd be very helpful for them. So they're very interested in this capability as well. Finally, as we try to predict the experimental values of the burning velocity, that means we have to properly compare the experiments with the calculation. That means we have to understand the experiments better. So we end up with better standards, more accurate, more tractable, more properly interpreted. So the process of predicting the experiments makes us learn a lot about the experiments and about the standard tests, which is very helpful for properly interpreting them. Is this an achievable goal? Well, if you look at hydrocarbons, we can predict burning velocities pretty well. Here's the left axis, is the y-axis is the burning velocity, adiabatic, planar, laminar, versus the equivalence ratio. The points are a bunch of different types of experiments at different labs all over the world. The predicted value, the measured value in the experiments. And the dashed line is a numerical calculation from first principles with a detailed kinetic mechanism. And as you can see, you can predict burning velocity pretty well. The interesting thing here is as we get to lean conditions, near the lean flammability limit, which would be out here at about 0.5 equivalence ratio, the disagreement gets a lot larger, and that's because it's harder to predict things at the lean limit. And unfortunately, this region down here is what we're trying to do with the refrigerant. So it's a much harder problem compared to hydrocarbons, but we still think we can make good headway and good contributions and move things forward. So what do you need to predict burning velocity? Well, you need a numerical model, one-dimensional, two-dimensional, steady or non-steady. You solve the conservation equations numerically for mass, momentum, energy, and species conservation with chemical reaction and radiation. We use detailed chemical models, not one-step models, not reduced models. We use detailed chemical mechanisms because if you want to understand extinction, if you want to understand flame propagation and ignition, you have to have a detailed model. So you need the kinetic parameters. You need the thermodynamic parameters for each species, all the intermediates and the reactants and the products. You need the transport parameters, the Leonard-Jones parameters. You need a radiation model, either a broadband model or, ideally a narrow line model. And you need the reaction rate parameters for all the possible reactions between all the possible species. So you need all the Arrhenius parameters for each reaction. Finally, you need these kinetic parameters in the chemists. If they get within a factor of 2 or 3 on the reaction rates, they're thrilled. Typically, they're within an order of magnitude or maybe 2. So we often depend upon experimental data for the system of interest to narrow down the uncertainties on the kinetic model, and then we compare the model with the experiment. So we need the experimental data both for kinetic model development and for seeing how well our model is doing when all is said and done. And that's sort of the approach. It seems circular, but it gives you, in the end, pretty good models that are very usable and fundamentally based. So it's not an unreasonable thing to do, and that's what this stuff is all very, very highly developed in combustion, and they can predict all kinds of things, and this is the approach that people use. So it's not unreasonable. It's state of the art. We've put together a really great team. There are 3 areas: kinetics, numerical modeling, and experiments. And all of those are represented both by people at NIST and people at universities. At NIST, the only full-time person with internal money supporting this stuff is me. Everybody else is basically supported by money we've gotten from the Department of Energy and the Army. But we have a great team, which will probably disappear very soon because the funding's running out. But for the time being, for the next 6 or 9 months, we're still going strong. We've got 3 great kineticists who are really the best in the world at what they're doing. We have a postdoc and a numerical guy who's also very good. We collaborate with a lot of universities. We are giving money to Heinz Pitch at RWTH Aachen, who is one of the top guys in combustion now. All the other people we collaborate because they're just interested in the work and they're willing to collaborate and work with us, and we're really, really fortunate to have them on board. We have active collaborations with industry groups and standards organizations. I'll talk a little bit more about that later. So this is a picture of the lab. I should mention that I was in fire research previous to being with the Energy and Environment Division now, and I was doing combustion research related to fire suppressants. Turns out a lot of these fire suppressants are also refrigerants, R125, 1234. 2-BTP is just like 1234YF except with a bromine instead of a fluorine. So I did this for about 20 or 25 years studying fire suppressants, particularly for aircraft applications. And so the transition to flammable refrigerants made a lot of sense, and that's what I'm working on now. We have a lot of different combustion experiments. I'll tell you about 2 in particular, these 2 on the table right here. I wanted to show you them in the lab to give you a sense of the scale of the experiments. This one's about 1.5 feet in diameter. This one's about 1 foot in diameter. And this is the first experiment. Well, no, I'm sorry, this is the 2 experiments. This one here is a 30-liter chamber, about a little more than a cubic foot, and has windows in it, and we image the flame. We call it constant pressure because the flame only grows to about the size of a golf ball at the largest size, maybe a tennis ball under some conditions. And so for this large chamber, the pressure rise is only about 1%, and we can consider it constant pressure. And we image the flame, and we take pictures of the flame at high speed, and that's how we get the rate of growth of the burning of the radius. This other experiment on the right is about a foot across in this dimension, and it's a sealed volume. We ignite it. Both of these we ignite. It's a pre-mixed mixture of refrigerant and air. We provide it with a high voltage spark in the center that ignites it, and you get an outwardly propagating spherical flame in both cases. In this one, we take a picture of it. In this one, we measure the pressure rise, and from the pressure rise, we can figure out what the rate of growth of the flame radius is. This is the first experiment, the constant pressure experiment. Couldn't a top view. We have a light source, parabolic mirrors. They shine through, we get parallel rays going through the chamber. We have a high-speed camera, a couple thousand frames per second. And this is a methane flame with 1% halon 1301. And you can see the flame growing over a times of about 33 milliseconds to a radius of about 4 centimeters. And we get these beautiful spherical flames under the ideal conditions. This one is ignited in the center, so you can see it's a nice spherical flame. In this experiment, the constant volume experiment, we get a pressure rise as a function of time. You know, the flame is small, so there's not as much pressure rise. Then we get a lot of pressure rise when it gets near the wall. But at this inflection point, when it gets near the wall, we start to have heat transfer to the wall. So we have to crop our data to cut off the ignition because we have a lot of ignition disturbances. And then we have to cut it off once it starts interacting with the wall. We turn that into the flame radius versus pressure or time with this thermodynamic model, which I won't go into too much detail on, but there's various techniques for doing that. And we have a nice tool now that we can give out to people who want to do this experiment themselves. In the end, we get burning velocity as a function of time, or burning velocity of a function of temperature and pressure shown on this three-dimensional plot. As the temperature goes up, or the pressure goes up, the temperature increases because it's an isenthalpic compression, and so we actually get the burning velocity as a function of those two parameters, which is great because we get data for a whole range of temperature and pressure, which is helpful for model validation. We do the experiment at 3 different initial pressures. We fit a surface to that, and then we extrapolate back to the initial room temperature conditions. Status. So here, this is where we are now. We've got we had kinetic mechanisms left over from the fire suppression work. But, you know, in fire suppression, you're adding small quantities of the fluorocarbons to large quantities of hydrocarbon in a flame, and the chemistry is different. So we had to update that mechanism and consider reactions that we didn't have to consider before. And we've really done a good job of moving that forward. We have a usable mechanism for 1-carbon and 2-carbon HFCs, including these compounds. And it also includes the fluoropropanes, 1234YF and ZEE and 1243ZF. This mechanism, and it's a combined mechanism, works for everything simultaneously now. Has about 1,000 reactions and about 120 species. And eventually we want to reduce this mechanism so it can be used in 3-dimensional codes. Right now we can use it in a 2-dimensional code, time-dependent with buoyancy, but it takes a long time, and you have to do it on a supercomputer. So that's we'd like to get it smaller. But first you have to develop, the complete mechanism. This picture here shows you what we end up with. This is the behavior of 125 in the fire suppression, a methane air flame. If you add 2, 4, or 6% 125 to this methane flame, this is the major reaction pathways. There's the actual, we have 120 species, so this is only showing about 10 or 20% of the actual reactions that happen. But these are the major reactions, and you can trace the path The thicker lines show you where most of the reaction is going. The different numbers show you what fraction of this species reacts with that reaction. So here, unimolecular decomposition popping off HF is most of the reaction of this 125 forming this compound here, and then that reacts mostly with reactions with hydrogen atom. The different numbers are the different concentrations of the 125 in the flame. So you can really get a good sense of what the important reactions are, and this tells you all kinds of things, and you can evaluate the effects of different things like humidity or temperature or pressure on what the reaction pathways are. So how are we doing? This is a plot of the measured burning velocity versus the concentration of that refrigerant in air. And this is 32, for example, a few different experiments. These are some old predictions. The lines are the predictions from the numerical calculation based on first principle with this detailed kinetic model with a one-dimensional steady model planar. So here's R41. Methane I showed you before. We can predict that pretty well. R32 is okay. Here are the two carbon species. We can predict them pretty well, not unreasonably for the first cut of our mechanism. This is the adiabatic flame temperature also plotted on the same plot. As you can see, the temperature of these refrigerant flames are nearly as close to the hydrocarbon flames. Here's ethane, and here's our, as we add more fluorines, the temperature comes down a little bit. Here's methane, and the adiabatic flame temperature is high, which implies higher reaction rate, but because the fluorine chemistry is slower, we're, a factor of 2 or 3 or more lower than the hydrocarbon burning velocities. So we're doing okay. Here are the fluoropropanes, and in this case, we add different amounts of oxygen to the air to give us a range of burning velocities, because these things sometimes start off a little slow. So here's the 1243ZF with 25, 21, and 18% oxygen. 21% oxygen, of course, is typical air. You can see we can predict these burning velocities reasonably well. Here's YF with 50%, 45%, 33%, and 21% oxygen. At higher burning velocities, where we're up around 10 or 15 centimeters per second, we can predict it pretty well. As we get down to air, we're off by a factor of 2 or 3 or more in the burning velocity. I'll talk more about that. We think our calculations are right. We think the experiments are wrong because they've neglected some important effects that occur at these low burning velocities. Here is a calculation at elevated temperature, 60 degrees C with YF or ZEE, where we add increased amounts of water vapor, quite a bit because it's at the higher temperature, up to 10% water vapor. You can see, even in the experiments, we increase the burning velocity quite a bit, from about 2 centimeters per second up to about 10 for YF. Our calculations, as I mentioned before, predict a much higher burning velocity. At the low end, we think our calculations are correct, but we show a similar sort of variation with water vapor, which is great because we can really, hopefully, start to understand why water vapor has this catalytic effect on these flames. Usually you think of water vapor as putting flames out, but in this case, it makes the flames burn a lot faster, and we think we understand why. I could talk about that if you're interested. Here is a plot. So in these plots, we can pick off the peak experimental and the peak calculated burning velocity for all the systems that we've calculated so far. If you plot them, we get this. Here's the calculated peak burning velocity versus the calculated measured peak burning velocity. The measured peak burning velocity. And that the dots or the values, the line would be equivalents. And generally, we're pretty good at the higher range. We're off significantly at the lower end. And of course, unfortunately, all the manufacturers are looking at things down in this range. And so things get really interesting there. Ultimately, we hope to have a predictive tool that people can use like RefLeak or RefLeak or RefProp, that you can tell it what your reactants are, what your oxidizer is, what your equivalence ratio is, what your pressure is, your initial temperature, what type of calculation right now. So we've got this thing working with the mechanism we have, and you could use it to predict these things I showed on this previous plot. ultimately we think it would be a nice tool to have, and it all depends upon having a good kinetic mechanism and understanding the caveats to the prediction. So I mentioned the Lactino Agreement at the lower end. This is why. First, there's this thing called flame stretch. Basically, if you have diverging streamlines through the flame, which you get if you have a curved flame, it affects the burning velocity. This is a plot of burning velocity versus radius. And you can see for this lean flame, this small flame here, you get a factor of 2 difference in burning velocity just because of the radius going from 1 to 3 centimeters. That effect doesn't happen for rich flames. Here, there's no variation. This is a well-known effect in combustion, and people aren't considering it in the refrigeration industry, but it can have a big effect on the flames, this effect of curvature or stretch. Buoyancy. The flame is distorted. Here's a flame which is not distorted that much, a little bit. It's ignited below center, and you can see it ends up centered here, but it's still pretty spherical. Here, it's distorted more. Which radius do you use? People have said we'll use the side radius, but we're doing some calculations that show that might not be good. Here's a YF flame. This flame is treated as a spherical flame with just looking at the side of the flame, the propagation outward. But as you can see, if the curvature is important, that could really affect it. Finally, radiation. People have done measurements and calculations for hydrocarbon flames, and they've plotted the actual results with the points and then fit a curve to that. This is the correction due to radiation versus the flame speed. And as you can see, as you get down below about 7 centimeters per second, the correction becomes huge. The same thing will happen for refrigerants. Actually, the correction should be higher because we have more of the radiating species in the refrigerant flames. So this is an effect which has not been taken into account for the refrigerant flames, and we believe you need to. So we're trying to move things forward and understand all these things and predict the right things. In the future, we'll add more refrigerants to our kinetic model. We'll keep improving the kinetic model. We'll get more experimental data to validate things, particularly with blends. We'll try to improve the radiation parameters, which for now are just approximations for the species that we can get data on. And then finally, we'll do more. We've done a lot of direct numerical simulations of the experiments, and we'll do more of that to understand the accuracy and the complications. Thank you. And hopefully we'll take questions if we have time.
Greg, thank you very much for that informative presentation. Very much appreciated. We've got a couple more questions, Ahmad, for you. I see that you've answered many of them online. So folks, if we don't get to your question, we are trying to answer them in the question and answer box. But we'll go ahead and answer as many of these as we can on lines for other people to hear them. If we don't get to them all, again, if you give us your email, we will try to answer you by email if we don't get to them today. Ahmad, there was a question around the physical dimension of the leak source that you were using in your modeling, and kind of how you arrived at that. So if you don't mind speaking to that, that would be very helpful.
Sure. So when we did our experiments to which we validated the CFD results for, we had to choose an equivalent diameter in the simulations to get to the experimental results to have better match, and that was 1 square inch. We are doing now sensitivity analysis to see the effect of the area on the concentration and flammable volume. But if the intent of the question to see if we're simulating small pinhole or small crack leaks, we're not. We're dealing with severed lines, leaks.
So more catastrophic, Ahmad, is kind of
Yes.
what the modeling was addressing?
Yes.
Yep, thank you very much. Greg, I just wanted to ask you a little bit, you talked a little bit about this issue for Australia. So there will be, continued recovery of mixed streams of refrigerants. And so could you talk a little bit about, facing this challenge around understanding how flammable those mixtures are and how to address them from a practical perspective, shipping and handling those refrigerants. Could you talk a little bit about how the model might be able to, kind of predict that in the future?
Well, so if you have some mixture of refrigerants with, some amount of 125 and some amount of 32 and some amount of 134A, because our model is fundamentally based and we have all these species in there, it should be able to capture the different mixtures. It should be able to capture the different mixtures and predict their burning velocity reasonably well. And so I think the real benefit is that it's fundamentally based, and that even if we haven't tested it for that particular mixture, if we validated it at a certain number of other conditions, it would it's not like an empirical correlation. If we interpolate between measured conditions, it should work reasonably well. So someone could say, okay, we've done a GC analysis. We know that our truck has this amount of 125 and that amount of 134A, and you could run a calculation pretty straightforwardly and get in the ballpark of the burning velocity, even just with what we have, after we validate it a little more and keep working on it. But it's certainly I would have a lot of I would feel comfortable doing that as a guiding tool. Does that answer your question?
Yeah, no, thank you. That's very helpful. Ahmad, I have another one for you. I'm wondering if you could tell us if the CFD included any potential local pressure and temperature changes, and if so, how they were addressed.
Yes, so the initial condition is ambient pressure, ambient temperature, and I want to say it was in the 24 Celsius range. The temperature, the leak was the saturation temperature of R32 at ambient pressure. And during the simulation, the CFD code updates the pressure and temperature of each cell based on the flow of the refrigerant, of the species mixing.
Thank you very much for that, Ahmad. Greg, I think we've got time for one last question, and this one's for you. I'm just wondering, we have someone asking if you could talk a little bit more about why water vapor increases flame velocity. They were interested in that.
Okay, great. This is my training as a combustion scientist. Basically, hydrocarbon flames are fast because they have high radical concentrations. The radicals are the fragments of water. So H, OH, and H atom. O, OH, and H atom are what attack the fuel and break it down. And these things reach really high concentrations in flame, much higher, like 2 orders of magnitude higher than their equilibrium levels. And that's what makes hydrocarbon flames so fast. And refrigerant flames don't. The fluorine atom combines with the hydrogen and lowers the radical concentrations, and so it shuts off the chemistry that makes these flames go so fast. But if you add water vapor, it acts as a source of HO and OH in the flame again, because the water vapor goes into the system, the fluorine atom attacks the water vapor, and you get HF and OH, and then the OH reacts with other things. So you basically increase the concentration of these reactive radicals in the flame, and the flame, even though you'd think it would put fires out, no, the fluorine's really active. You get super high concentrations of fluorine atom in the flame. It attacks the water vapor breaks apart. You get these radical concentrations go up, and the flame starts to act more like a hydrocarbon flame again because of the radical concentrations. You already have high flame temperatures, So if you can increase the radical concentrations, the thing is going to act more like a hydrocarbon, and that's why water vapor does it. It's really complicated, though, because sometimes you add water vapor and it doesn't have. I'll go into it later, but we can understand it, but we have to understand all the different intermediates in the particular system because they behave differently depending upon what you have, and we can talk more about that. But that's why it augments the combustion. It increases the radical pool of radicals typical of a hydrocarbon flame.
Thank you so much, Greg. Ahmad, thank you. Philip Johnson, thank you so much. Really appreciate all the effort that goes into the work behind the scenes and presenting for the many stakeholders that are participating in this webinar. Just to the attendees, join us next week for the last installment in this series of webinars around refrigerant research. We'll be meeting again next Wednesday at the same time to have a discussion around combustion of refrigerants. Thank you again, and you can see this presentation repeated online on our website here in the next couple of days.